Okay, this is the first page of this worksheet. Let's have a look. We have to work out how much mechanical energy this person has over here. Can you all see that? Yeah? Okay, yep. Right, so if you've already done it, then you can follow along just to make sure you did it right. But let's go through the ideas. So this person is 60 kilos, moving at 8 meters per second. All right, so when we look at our data sheet, we can say that we've got an M and we've got a V. Which equation should we use, please? Alex? To work out the kinetic energy.
The first one, kinetic.
Yep, good. The kinetic energy equation, which is, call it out.
Ke equals half m times v squared.
Okay, so that's the one that's on the sheet there. EK also on your data sheet, but that's fine. All right, so we substitute in the mass, which is 60. We substitute in the velocity, 8 squared, and we can work out his kinetic energy. So that'll be 1920. All right, joules. Excellent. Now we see that he's on the floor, so his potential energy is 0 joules. And so therefore, his kinetic energy and his mechanical energy, which is the total of the potential energy and the kinetic energy, is 1920. Correct. All right. So 1920 joules. Now remember, the mechanical energy is the same everywhere he is. The mechanical energy is the same everywhere he is, assuming that there's no friction. So the first thing you can do on the other two diagrams is write out his mechanical energy. 1920 joules. Okay? That's the first thing you can do. 1920 joules mechanical energy. All right? So, now let's have a look at the next part of the diagram. Now the skateboarder is 1 meter off the ground. And if he's 1 meter off the ground, now he has some gravitational potential energy. Let's work out how much gravitational potential energy he has. So we use the other equation, GPE or EP, for the gravitational potential energy is equal to mgh. So his mass is 60, gravity is 9.8, and his height is 1 meter. Okay, so 60 times 9.8 times 1, 588. 588 joules. Now here's the key idea. The kinetic energy and the potential energy have to add up to the total mechanical energy. So I should be able to say that the EK is equal to 1920 subtract 588. Because the kinetic energy and the potential energy have to equal up to the mechanical energy. So, what's that? 1920 take away 588. It's 1332. 1332 joules. Okay? 1332 joules. But now we're asked to find his velocity. So now, which number should I use to work out his velocity? I should use which energy? Potential, kinetic, or mechanical? Not mechanical. Not potential. So the kinetic energy. So the kinetic energy is the one that I'm going to use to work out his velocity. Because if you look at the equations at the top here, only one of them has velocity in it, which is the EK. So now I have EK, I have his mass, I can work out the V. So, that equation, V is equal to 2 times EK over M, and then square root that. Okay, so that is the rearrangement of that equation. So, if that's the rearrangement of that equation, it is going to be 2 times what? 2 times 1332. That's his kinetic energy. It's only the kinetic energy, not the mechanical energy. Then divided by his mass, 60. So 2 times 1332 divided by 60 is 44. Is that it? Is it 44.4 meters per second? No, I got to do what? Square root the answer, which makes it 6.66 meters per second. Okay. Then the last one is implying that the skateboarder has reached the highest point that he's going to get. So, if he's reached the highest point that he's going to get, therefore, his potential energy, all his energy is going to be potential energy. All his energy is going to be potential energy. So, that's the highest point that he's going to get to. So how much kinetic energy is he going to have? Zero. And that makes sense because at the top of any particular arc, you stop moving. And if you stop moving, all of your energy is potential energy. That means we can work out either the V or the H is going to be 0. Which V or H is going to be 0? The V, because he's not going to be moving. He's got a 0 meters per second because he's stopped moving. Now the question is, how high off the ground is he?
3 meters.
So he's not 3 meters off the ground. So let's have a look. Which equation should we use to solve for H? Which equation? The gravitational potential energy is the only one with the H in it. So what we're going to do, we have to rearrange the equation to get H. H is equal to EP over mg. Okay? So that's the rearrangement of that equation. I can substitute in values. What's my EP value? 1920. All of the energy there. His mass is 60 times 9.8 as g. And so 1920 divided by brackets, 60 times 9.8, close brackets, 3.26 or 27 meters. Okay, 27 meters. So, key ideas. Mechanical energy is same everywhere, or constant everywhere. Those are the key ideas. Then, if you know that the mechanical energy is the same everywhere, you can use that idea with this equation at the top to work out the other kinetic or potential energy if you've got one of them. Okay? Let's look at the next one. Look at the next one. So here, right? So it's some sort of ball roller coaster. Let's go start out what this thing will do. So at position number 1, so this is now position number 1, we can see that the ball is not moving, or it doesn't say it's moving. It's 4 meters above the ground and it's got a mass of 50 kilos. So we can tell that it has a lot of what type of energy? Potential or kinetic? Potential energy. So because it has a lot of potential energy, we should use the EP is equal to mgh equation to work out how much energy it has. Okay, so substitute in those values, 50 times 9.8 times 4, which is 1960 joules. Now, do I make that 1960 across all of the potential energies? No. Right? What's going to be the same across all of them? The mechanical energy. So, they're all going to be the same. The mechanical energies are all going to be the same. But we also know that this thing has no kinetic energy at the beginning. So, that's going to be 0 joules. It's not moving. So, its mechanical energy as the total between the kinetic and the potential is going to be 1960. And then immediately we can say, okay, 1960 all the way across. All the way across. 1960 all the way across. Right? We can also work out its velocity as 0 meters per second at the beginning. So now we have to look at position number 2. So we find position number 2, it's over here. Position number 2, Now we're looking at situation number 2. Now, the ball is rolled down this, gone up the loop-de-loop, and at this point, it's going to be going at some speed, but it's also got some potential energy as well. Some potential energy as well. So, which one can we work out? Can we work out the potential energy or the kinetic energy first? The potential energy, because we have what information? The height. Good. So, we're going to work out the potential energy, right? How do we work that out? Do I need to rearrange the equation? No, I do not. So, I'm going to say that it is EP is equal to mgh again, because I got the height, I got the mass. So, it's going to be mass 50, g 9.8 times the height 3. Right? 24/7? That doesn't sound right. 1350. No, that doesn't sound right either. 1470. Okay, so now that I've got that, what other number can I get now? I can get the kinetic energy. How do I get the kinetic energy? 1960 subtract 1470, which is equal to 490 joules. Whoops. 490 joules. So now that I have 490 joules, what can I do with that value? I can work out the velocity of this object. What is the equation for velocity? V is equal to, who remembers? Square root 2 times EK over M. So now I'm going to substitute in those values. So the EK is 490 and the M is 50. Okay, so 2 times 490 divided by 50, square root that answer, 4.43 meters per second. Okay, now we look at position number 3. Position number 3 is at the bottom. What information does that tell us? It's got no potential energy. Good. 0 potential energy because it's at the bottom. What other information does that now tell us? Not its velocity. It's got kinetic energy of 1960. All of it is kinetic energy. So now we have to work out the velocity of this thing now. So again, V is equal to the square root 2 times EK over M. Substitute the EK, 1960. Substitute the M, 50. And we get 2 times 1960 divided by 50, square root that answer, 8.9 or 8.85 meters per second. Okay. So now, here, in the last situation, situation number 4, we are now given its velocity. What can we use that to work out? Find the height, but how? What's the first thing I need to do? I need to work out the kinetic energy. Good. So, the equation for kinetic energy is EK is equal to half mv squared. So it's half times 50 times v squared, which happens to be 6 squared. So what do I do? Half times 50 times 6? Squared. Don't forget the squared. And that happens to be 900 joules. Is that where I write it? No. Where should that go? In kinetic energy. Oops. 900 joules. So what does that mean about my potential energy? 1060 joules. Excellent. So now how do I work out the height? I have to rearrange the equation. Who remembers the rearranged equation? Height equals EP over mg. So I substitute that. So I write out 900 over 50 times G. Is that right? No, I've got to pick the EP and not the EK. Right? So it's 1060 over that. So 1060 divided by bracket 50 times 90, close bracket. 2.16. 2.16 meters. Okay. So, key ideas. Mechanical energy is always the same. Then, you use the information to get either potential or kinetic energy, and then you solve the other. Stop. Key idea. At the bottom, it's always going to have zero potential energy. At the top, it's generally going to have zero kinetic energy. Sometimes it can have some kinetic energy there. Let's have a look at the next. All right, so let's have a look at question number 9. A 74 kilogram student starting from rest slides down an 11.8 meter high water slide. How fast is he going at the bottom of the slide? So, I might draw a quick drawing of this thing. Here's the slide. Here's the person. Okay, his mass is 74 kilograms, and he's up an 11.8 meter slide. Now the question is, how fast is he going when he gets to the bottom of the slide?
0.
So, stop. The idea is that he starts off with what type of energy, Giuliano?
Wait, 1 second. Potential energy.
He starts off with potential energy. All right? But we've got to work out how much kinetic energy and how much mechanical energy he has at the start. So, let's go through this idea. How do I work out his potential energy at the start? What equation should I use? Robin. What's the equation for gravitational potential energy? mgh. Excellent. All right? So, now what we're going to do is we're going to substitute in those values. So we know his mass, that's 74. We know his gravity, 9.8. We know his height, 11.8. So 74 times 9.8 times 11.8 is 8557.36 joules. Okay? Where do I put that number? I put that number into EP here. 36 joules. What should I put in the kinetic energy at the beginning? What should I put in the kinetic energy at the beginning? 0. How do I know it's 0? How do I know that the kinetic energy is 0? What is his kinetic energy? How do we know that his kinetic energy is 0? Because it's at the start and it says that he's at rest. So rest means he's not moving, so his kinetic energy is 0. So what's his total mechanical energy? What do you think? 8557. 8557.36 joules. So, which one of these is always going to be the same? Mechanical energy. So, if his mechanical energy is going to be the same, it's going to be 8557.36 joules. Okay? However, he's at the bottom of the slide, so one of these values is going to be a 0. Which value is going to be 0 now that he's at the bottom of the slide? EP. Now he's going to have 0 potential energy. That means we know something about his kinetic energy. What is his kinetic energy going to be? Up? How much up? 8557.36 joules. All of it is going to be kinetic energy. So now we need to work out how fast is he going. So, to work out that out, we can use the equation V is equal to the square root of EK over half times M, which is just a different version of 2EK over M. Okay, so if I do that, then I do all the EK, 8557.36, divided by bracket, half of his mass. So half times his mass, right? And then I square root the entire thing, and it's going to be 15.2 meters per second, right? So that's how fast this person is going at the end, 15.2 meters per second, right? Because all of his energy was converted into kinetic energy. Now let's have a look at the next question. Calculate the kinetic energy of a 750 kilogram compact car moving at 50 meters per second. That's a bit easier. So now the equation EK is equal to half air times M times V squared, because it's just asking for kinetic energy. So half times 750 times 50. Is that correct?
Yes. You gotta square.
I have to square what?
You need to square the 50.
Square to 50. Okay, so 0.5 times 750 times 50 squared is 937,500 joules. Okay, now let's do number 11. Okay, so number 11.
So you go up a bit.
Okay, so determine the mechanical energy of a 450 kilogram roller coaster moving at 30 meters per second at the bottom of a first dip, which is still 15 meters above the ground. So, here's my roller coaster, bottom of the first dip, which is 15 meters above the ground, right? And the roller coaster thing is moving at 30 meters per second, okay? And it has a mass of 450 kilograms. Okay, so let's remember, I have to work out EP, EK, and EM. So we're going to have to do three different things. We're going to do the potential energy first. So as potential energy, the equation is mgh. So what's his mass? What's his mass? 450. What's gravity?
9.8.
And what's the height that he's at?
15 meters.
15. So 450 times 9.8 times 15. So that's 66150 joules. 66150 joules.
Same for the EM.
Same for the EM? So it's 66150 joules? No, because this object or this roller coaster is moving. So it's moving as well. So we have to use that moving to get out the EK, and then we can work out that one there. Right, so now let's work out the the EK. So EK is equal to half mv squared. So what's half? It's half times the roller coaster's mass, which is 450, times its velocity. 30, just like that? No, you got to square it. Good. So 0.5 times 450 times 30 squared equals 202,500 joules. So now it's 202,500 joules. Okay? And then we add them together, plus 66150 equals 268,650 joules. Okay, and that's the total mechanical energy. Remember, if he's moving and he's a certain height above ground, then that's going to have both types of energy, and we have to work out the thing. Now look here. Look at the board. How much mechanical energy would he have at this point here? 268, 650. Yeah. How much mechanical energy would he have here? 268, 650. The mechanical energy is the same all around. Here's a question. How much potential energy? 0. How much kinetic energy? 268, 650. How much potential energy here? 650. Good. And then 0 kinetic energy. All right. So, Julie has a mass of 49 kilograms. What is her potential energy when she's standing 6 meters up a diving board? And then Julie jumps off the diving board. Okay? So, this is the diving board. This is Julie. Right? Her mass is equal to 49 kilograms. Right? And she's 6 meters above the ground. Okay? So, she dives off. Now, what you should realize is that at the point of diving, and when she's just about to land into the water, all of her gravitational, she'll have lots of gravitational energy here, but no kinetic energy. Right? But at the bottom, she has no gravitational potential energy, but she has lots of kinetic energy. And so we're going to convert all of that gravitational potential energy into kinetic energy. That's how we're going to solve this problem. So, let's work out, first of all, what is her potential energy when standing on the 6-meter diving board? So, that is EP is equal to mgh, right? Her mass is 49, her gravity is 9.8, and the height is 6. So 49 times 9.8, 49, to what? 2881.2. Okay, so we've got that potential energy. Now, all of that potential energy is going to be converted into EK. All of that potential energy is converted into kinetic energy. So now the kinetic energy is 2881.2 joules. So then that's the kinetic energy she has just before she hits the water. So then now we say, what's her speed? What's Julie's speed? So now we say, okay, what's the rearranged equation? V is equal to EK over half m square root. All of it. Okay? So 2881.2 over half of times 49, and you square root the entire thing, right? 2881.2 divided by brackets 0.5 times 49. I want you to type that into your calculators, and I want to see if you can get the same number as me, because if you can't get the same number as me, you need to learn how to type that into a calculator. So 10.84 is the correct answer in meters per second. All right? So that's the idea behind these conversions of energies, right? There's going to be some mix of mechanical, kinetic, and gravitational potential energy, right? But for now, let's move on and do some of the Newton's laws. So I want you to get out the worksheet that says Newton's laws, and let's go through some of these ideas. So, this diagram here is a nice way of summarizing all of the information. You have the first law, right? Which is inertia, which means objects tend to keep on doing what they were doing before unless they're acted on by an unbalanced force. Then we have Newton's second law, which is more force means more acceleration, or more mass means less acceleration. Okay? And you can use the equation F is equal to ma. Right? And then you have third law, right? Each force acts as a pair, and there are always equal and opposite. Okay? Forces act in pairs. Forces act in pairs, and they are always equal and opposite. So those are our three laws. Okay? So let's have a look at this question here. If you use the same force on a less massive object, what happens to the acceleration? So the words less massive just means less mass or a lower mass object. So if you push something that is heavy and you push something that is light with the same amount of force, what happens to the light object's acceleration? What do you think? It will be increased. Good. So there is a more acceleration on the lighter object. Okay? So, what causes an object to speed up or slow down? What causes an object to speed up or slow down? Any ideas? So let's have a look here at the Newton's 3 laws. We should know that objects moving should keep moving. So what all causes it to slow down? Must be an unbalanced force. What is the name of the force that acts against motion? Starts with F. Friction. Or air resistance, things like that. So friction slows things down. It's the unbalanced force which slows things down. Right? Okay. So friction, which is the unbalanced force which slows things down. Okay? Nope, not that one. Let's have a look at the next one. Right, let's have a look at these questions here. Okay. Let's do this question here. You're on a line for the diving board in the local pool. You watch people dive into the pool from the board. You realize that a diving board to spring in the air is a good example of Newton's third law of motion. Explain how a diving board illustrates Newton's third law of motion. So let's have a think. All right, here is the stand, here is the diving board, here is the person. Okay? When a person jumps up and down on this thing, what happens to the diving board? It springs or moves around. Okay, so you might jump up, and it will bend. Right? The idea is that when you push down on it, a force is acting back upwards on you, right? Pushing you up. Okay? So, if you're in this position here where you're about to dive in and the board is in this bent position, what forces are acting upon you at that point? There's gravity acting on you. Good. So the number one force that's acting on you is gravity. What else? What other force is about to act on you as you're standing on that bent board? Applied force from the board. Do you think that applied force is going to be larger or smaller than the gravity force? Yeah, larger because it's going to have elastic energy as well. This is due to the elastic nature of the board. Okay? So, but the idea is that as you bounce up and down on the diving board, you're pushing it down, it's pushing you back up, right? The applied force at this point will be much larger because of the elastic forces that are acting on it. All right? Let's have a look at this one here. Okay, let's do this one. Your shopping cart has a mass of 65 kilograms. Question number 5. You push it, in order to accelerate it down the aisle at 0.3 meters per second squared, what force do you need to apply to the cart? So, this is a calculation. Which equation should we use? Look at your data sheets. Which equation? Look at your data sheets. Which equation? What do you think? Force equation. So, what's the force equation? M times A. So, mass, 65. Acceleration, 0.3 meters per second per second. So 65 times 0.3 is what? 5.85? No? 65 times 0.3. 19.5. And what's the unit for force?
Meters per second.
Newtons. Newtons is the unit for force.
So when do you use joules?
So joules is for energy. So the kinetic energy, gravitational potential energy, and mechanical energy, and also work. All of those are joules as the energy idea. All right. Let's try the next one. Small child has a wagon with a mass of 10 kilograms. A child pulls on the wagon with a force of 2 newtons. What is the acceleration of the wagon? So we've got to use this force equation again. But we have to rearrange it, correct? So what is the rearrangement? We want to have A. So how do we rearrange that equation, Taj?
Force divided mass.
Force divided by mass, good. The force is 2, the mass is 10. The acceleration will be, not 5, 0.2. The other way around, 2 divided by 10, not 10 divided by 2. Okay, so 0.2 meters per second, yeah?
Number 5, when it says 0.
Let's go look at the next page. Here, let's do this one. Going back one page. Jane drives to work. Okay? When Jane drives to work, she always places her purse on the passenger seat. By the time she gets to work, her purse has fallen on the floor in front of the passenger seat. One day she asks you to explain why this happens. So why does the purse on the passenger seat always fall to the floor? Yes, Arvidsson?
It's inertia. She's making it go forward when she brakes.
Okay, so inertia makes the purse go forward when the car brakes. Now, there's a couple of things that can be added to that. So, the idea is that the purse going forward, let's have it put a little bit more detail to that. The purse doesn't go forward, or it doesn't accelerate. It's staying at the same speed, all right? So inertia makes the purse continue to move forward. When the car brakes. Okay, so it's about the purse wants to continue to do so. When the car brakes, everything around the purse slows down whilst the purse continues to move forward. All right? So it's the idea that the purse will continue to move forward. All right? Page. So, right? So, let's have a look at this question here. An object's resistance to change in motion is dependent solely on what quantity? It's resistance to change. So you will change when you have a force applied to it, but how much you change your acceleration is dependent on what? So its force is equal to ma, right? What property of the object determines how fast it will go? Its mass. Its mass determines how fast it will go. What is required to cause acceleration? Remember, you're going to keep on moving at a constant speed unless acted on by an external force. So it's an external force. Okay, so let's have a look at this cart. Okay, one person pushes 5 newtons one way, one person pushes 5 newtons the other way. What is this cart going to do? Stay stationary. You're assuming it started stationary, so therefore it is staying stationary. Okay, so stays stationary. All right, if one person decides to pull instead of push, right, if one person decides to pull instead of push, what is the cart going to do? It's going to move, but how? 10 newtons, yep, good. So it has 10 newtons force, so it's going to move. Is it going to move at a constant velocity? No, it's going to accelerate. So remember, whenever you have an unbalanced force, it's going to accelerate. Okay, let's go on to the next set of questions. All right. Actually, there was a question that I wanted to get to. Where was it? I'm skipping a page, so this is now, right? The one with the graphs on it. Okay. So let's have a look. Let's do this one here. Suppose you were in space in a weightless environment. Would it require a force to make the any object move? Yes, you would. All right? So, the words set an object in motion implies that it started at rest. So, yes, you need a force. Okay? Right. Let's have a look at this question over here. Number 4. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed and in this direction? How much force is required to keep the object moving? Any ideas? 8? Nope. How much force is required to keep the object moving? 0. Why 0 force? Because it's got inertia. Inertia is going to keep the ball moving. But it does have to overcome the frictional forces. But in real life, it will have to overcome the frictional forces. Okay, so let's have a look at this graphing question. Okay, Luke, below, drops an approximately 5 kilogram object off the roof of his house of a swimming pool. Upon encountering the pool, the object encounters a 50 Newton upwards resistance force, assumed to be constant. Use this description to answer the following question. All right. Which of the following velocity time graphs best describes the object in motion? So let's have a look here. So, here is the ball. It's above the pool. It's acted on by a 50 newtons force. So, what is it going to do between this point and this point? Does it have a balanced force acting on it? Alex, close your computer and follow along. So it has no balanced forces acting on it. It's got an unbalanced force, so it's going to move at a constant speed, or is it going to accelerate? Okay, it's going to accelerate. Okay, so it's going to get faster, or it's going to move away from the velocity 0. So it's going to be faster, and then it's going to hit the water. Now, is it still going to be pulled down by gravity? Yes, but at the same time, it's going to be pushed back up by the water force, which is 50 newtons there. Okay, so it's going to be pushed up by the water force there. So if it's pushed down 50 by gravity and pushed up 50, is it going to stay at the same what? Stay at the same, those words are correct. Location? No. It's now got balanced forces acting on it. So therefore it's going to have the same velocity. It's going to stay at the same velocity. Because remember, it only changes its velocity when there's unbalanced forces. So it's going to accelerate. It's going to accelerate away and then it's going to stay at the same velocity. So it's graph B. Okay? So the ball in theory will not stop because it has balanced forces acting on it. Right?
Wait, so does that mean that it will just stay under the water?
Well, not it will stay under the water. It will stay under the water. It will continue to move down through the water. So imagine this is a shot put, not like a beach ball. Okay, so imagine you put it a shot put, it will hit the pool and continue to sink down, but at a constant rate. Because if you think about dropping a shot put, it will accelerate, get faster, 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 faster. But when it hits the pool, it's going to make a big splash, and it's going to have the water pushing up on it. So therefore, it's going to not accelerate anymore. It's just going to move at a constant velocity down. Okay? All right. Let's try this couple of these ones, and then we'll go to Newton's third law. So skip a couple of pages, go up to the page where it starts with question number 10. Okay, so we're doing question number 11. What is the acceleration of a 0.3 kilogram ball that is hit with a force of 25 newtons? Now remember, the mass of an object always needs to be in kilograms. So 300 grams is 0.3 kilograms, but you would need to convert it into kilograms. Okay, so what is the acceleration of this? What equation are we going to use? We're going to use F is equal to ma. But we need to rearrange the equation. We want to find A. So the rearranged equation is what? F divided by m. So 25 divided by 0.3. So 25 divided by 0.3, 83.33. Okay, whoops. Meters per second per second. All right, that's this acceleration. All right. Next, how much force is needed to accelerate a 68 kilogram skier at a rate of 1.2 meters per second per second? Right, again, force is equal to ma, but I don't need to rearrange the equation. So it's 68 times 1.2, 81.6. What's the unit? Newtons. Good. Newtons, because it's a force. Right. What is the mass of an object that requires a force of 30 newtons to accelerate at a rate of 5 meters per second? So now I want the mass, and mass is equal to F over A, 30 over 5, which happens to be 6 kilograms. All right? Okay. So those are the various versions of this. All right, and there are just continuing questions. Let's move on to Newton's third law, and let's go through some ideas.